Hey class, this is Mr. M, showing you some examples to help you with your homework. This example will help you find inflection points using an analytical method. Recall that an inflection point is where a graph changes concavity, and concavity is a change in the function's derivative. So a derivative changes, meaning we're talking about the second derivative. So in order to find this, you'll notice the method will be very similar to finding relative extrema involving maxes and mins and the first derivative test, except we're going to be using the second derivative instead of the first. And this will tell us where the function is not increasing or decreasing, but rather where it is concave up and where it is concave down. So let's take a look. The first thing to do, when in doubt, take the derivative. F prime of x is equal to 3x squared minus 2x. And if you wanted to find the maxes and the mins, this would be the place where you do that by finding the critical numbers and using an interval method or the number line to help you figure those out. But we're going to continue in a different direction and find the second derivative, which here would be 6x minus 2. We're going to find our terrace point, which is, or points I should say, which are similar to which are similar to critical points in that they may be locations of inflection points, but not necessarily. Just as relative extrema are always at critical points, but critical points are not necessarily relative extrema. Long story short though, find the second derivative, set it equal to 0, and find x. In this case it's obvious that x will equal 3. So this is an example of a terrace point. Well, that is not enough information to know it's an inflection point. We must figure out, is there a change in concavity on either side of 3? If so, then it's not only a terrace point, it is also an inflection point. So populate your number line with your terrace point or points. These are x values. We're going to plug them into f prime in order to find out information about f. Alright, so to show our intervals here more clearly, we have two intervals created, less than 3 and greater than 3. Plugging in a number less than 3 into, once again, you'll see here, into the second derivative. Let me get rid of that, just want to emphasize it. Into the second derivative. Plugging a negative number in, well, plugging it back into the second derivative here, 6 times a negative number will give you a negative number, minus 2 is still negative, so this will be a negative number. You could also plug in 0 to make it negative 2 and it becomes quite clear. A number on the other side of the interval, for example, 1,000 or 10,000, 6 times 10,000 minus 2 is quite obviously a positive number. So the second derivative is negative when it's less than 3, it's 0 at exactly 3, that's how we found it in the first place, and it's positive beyond 3. Which means that f's behavior is as follows. If the second derivative is negative, as we saw in our example in class, then f is concave down. Conversely, if the second derivative is positive, which is true on the other side of the interval, then f is concave up. So, to explain, find all inflection points. F has, I'm going to abbreviate here because of my small board, an inflection point at x equals 3 because, and here's the important part, because f double prime changes sign here. So recall, the AP test does not give credit for number lines. Number lines are a way for you to organize your information. A written explanation is valid justification. So to recap, we found our critical points, our terrace points, which are a lot like critical points. We plugged them into a number line in order to figure out what f double prime's behavior was, which was negative and then positive. And because of that sign change, you have an inflection point where the terrace point was at x equals 3.